Let's make a complicated situation or a seemingly complicated situation a little bit easier by using our good friend conservation of energy. So for this problem, we're going to start with a disk um, with a hole at about its center, but we're going to shift that hole off off center by a distance r. So we're going to drill a new hole right at the very edge of this disk. And then as a next step, what we're going to do is take this thing and kind of pivot it up off of that new point we've just drilled, and then let this thing swing back down. And our question is, what's the speed of the center of mass at the bottom? And we need to be careful. That's a sneaky, challenging question there, because it could ask us about the end, and we'll talk about that later. Okay. So to find the moment of inertia of this, well, first let me start by saying why it would make sense to look at this from a conservation of energy standpoint. And the big thing is just the complexity of this, okay? There's too many things changing to look at this from a net torque equals moment of inertia times angular acceleration standpoint. Because once again, the direction of the torque, not the direction of the torque, but the direction of the gravitational force um, relative to the rotational axis changes as this thing sweeps throughout. Okay, we have a changing angle of our force. It's way too difficult to deal with. Okay, so that's whenever the path is difficult and we're asked for speed, we want to think energy even in this type of problem. Okay, and for an energy analysis, we're going to need to know the moment of inertia. So we're going to have to do a little extra step in here, and that is start with the moment of inertia of our disk, but realize by the parallel axis theorem, if we offset our rotational axis, then we need to account for that by doing mass of the whole thing times how much you offset it squared and adding that to here. Okay, so here I made life easier. I offset it r, so it gives us a moment of inertia that we can express in m's and r's only. Okay, 1/2 mr squared plus another mr squared, and then that equals 1.5 or 3/2. Okay, so that's the moment of inertia we'll go forward with. All right, so we're raising this thing here up here. We're doing work, and whenever we tip something like this, okay, it's different than regular conservation of energy problems because we have to really focus our attention on the center of mass. Even if this problem wasn't asking us about it, the center of mass, we're going to think about it because how much height do we change the mass on this on average? Well, it's from where it started right here, where the center of mass is here to where the center of mass is at the end, and that's going to be 1r. Okay, so we teeter this thing up. That's our initial place right there. So we're going to drop this from rest. It has no kinetic energy to begin with. We're going to look at the bottom when all of that work we've done against gravity has come back and there's no potential energy left. Okay, so it still just looks like a potential equals kinetic kind of situation. So how much potential energy do we have? Well, raising this mass up, we're raising it 1 radius worth. Okay, sorry. In general, this is what we're thinking, all right? mgh equals 1/2 I omega squared because we're talking rotational kinetic energy here. And it's important. Even though we're talking about a single point, we're still going to look at the kinetic energy of the entire object first, okay? But here's where we have in terms of our problem here, if we can only use, G's and R's, and these should be big M's, by the way. Big MGR is our initial gravitational, and then we've got this over here, and like all rotational problems, we've got to do more. Okay, we've got to expand moment of inertia to what we found a second ago, which if you remember, it was 3/2. So 1/2 times 3/2 mr squared. Our angular velocity, well, we want to look at what the angular velocity of this point's going to be. Okay, so angular velocity relates to linear speed by v over r. In this case, it is just v over r. Okay, and what's important with that is we're not talking about the radius of the circle. That's a coincidence in this problem. We're talking about how far away is our point of interest from our rotational axis. So in other words, if we were instead asking how fast is this point on the bottom going to be going, oops, this point at the bottom, then it wouldn't be over v over r. It would be v over 2r because that's how far away that would be. All right. And then the path to this from this forward, once you've recognized it's an energy problem, once you've gotten this far, is just algebra, right? Like happens a lot when these, it's kind of satisfying. These r squareds go away, and we're left with something that sounds kind of like just regular kinetic energy, but with a new coefficient out front, 3/4 in this case. And then these gravity type problems, mass is going to go away. When we clean up our fraction and take a square root, it's going to be 4/3 g over r. Dimensionally, length times acceleration would be meters squared per second squared. Square root of that would be meters per second. So that looks good. And does it make sense that the speed would be greater for greater gravitational field strength? It does. The bigger r would mean it would take more work to lift this thing up, which would mean we would have expect more kinetic energy and or speed at the bottom.